Welcome to a reading from the Lucasian Legacy, the Lucasian Professorship of Mathematics at Cambridge University, 1663 to 1993, by Robert Bruen, as read by his son, Garth Bruen. Chapter 3, the 19th Century, Searching. We were about to try our strength under unknown conditions, and as the various possibilities of the enterprise crowded upon the imagination, a sense of responsibility for the moment oppressed me. But as I looked aloft, my heart lightened, and I remarked cheerily to Hurst that nature seemed to smile on our work. "Yes," he replied, "and God willing, we shall accomplish it." T.H. Huxley. Background. The 19th century was one of growth accompanied by growing pains. The British population of 1801 was about 10 million people, with London at about 865,000. By 1831, Britain had grown to almost 14 million, and by 1851, there were almost 21 million people, more than double in 50 years. In 1871, there were approximately 26 million. London itself, by 1881, had over 3.3 million people. In the previous century, Britain started with about 7.5 million and added about 2.5 million, an increase of 33%. In contrast, this century added over 16 million people for an increase of 160%. London added more people in this century than were added to all of Britain in the previous century, making London the largest city in Europe and almost 3 times the size of New York. Britain continued this growth in the next century to 42 million in 1921, before the rate of increase began to level off. In 120 years, Britain's population quadrupled, with all expected challenges appearing. War played an increasing role in Britain's daily life during the 19th century. In 1803, France and Britain started fighting again, and the Second War with the Maharatha in India broke out. In the following year, Spain declared war on England as well. The United States declared war on England in 1812. France and Turkey joined Britain to fight against Russia in 1854, and in 1856, the British War with Persia broke out. The following year, Britain was fighting in India and China. The government continued to grow, but not without problems. In 1812, Prime Minister Spence Perceval was assassinated in the House of Commons. King George III was declared insane and replaced by the Prince of Wales, who became Prince Regent. George did not die until 1820. Then the prince became King George IV, lasting only 10 years. His successor, William IV, was succeeded by Queen Victoria, who stabilized the crown by her reign into the next century. On the positive side, Britain passed progressive laws, such as the first Public Health Act in 1848, the Ballot Act in 1872, and the legalization of labor unions in 1871. The income tax was abandoned in 1815, but restored in 1842. The British managed to avoid the crash of revolutions that broke out in Europe in 1848 and 49, Rome, Paris, Berlin, Milan, Venice, and Vienna, which had 3. Social problems, however, were significant. The Luddites fought against the forward march of technology by destroying industrial machines in 1811. Beginning in 1815, the post-war economic crisis led to large-scale migrations to America and Canada over the next few years, and there were riots in Derbyshire against low wages in 1817. The failure of the Irish potato crop in 1846 caused widespread famine in Ireland, making life difficult for everyone. From 1850 to 1860, over 400,000 people from Britain and almost 90,000 people from Ireland emigrated to America to seek a better life. Industrial technology moved increasingly into the public life during this period. Gas lights were first installed on London streets in 1807, and in 1814, the first district to have gas lights was St. Margaret's, Westminster. The Atlantic cable to America was completed in 1865, providing telegraph services between Europe and America. Britain's growth during the 1800s provided an amazing backdrop for the events at Cambridge. It is not surprising that the Lucasian chair was as volatile as the rest of the country. The 1800s saw the beginning of a revival of mathematics in England, due in part to the Analytical Society at Cambridge. The society was either a precursor to the revival or a direct contributor to it, depending on the source consulted. Certainly it had some effect, even if it was limited to the involvement of people such as George Peacock and Charles Babbage. Both were members of the group of undergraduates and recent graduates that formed and operated the society. Later, Babbage would become a Lucasian professor and man of renown. The 19th century was a period of searching for an identity and stability, as the Lucasian chair saw holders who were no longer simply mathematicians, but were involved in other fields that used mathematics. This century saw a man calculating fluid flow, an astronomer, a man inventing computing engines, as well as the return of excellence to the Lucasian chair. The search was successfully concluded. Whittaker has made an observation on Cambridge during this century that is indicative of the situation. A few years before Green published his first paper, 1828, a notable revival of mathematical learning swept over the university. The fluxional symbolism, which since the time of Newton has isolated Cambridge from the continental schools, was abandoned in favor of the differential notation, and the works of the great French analysts were introduced and eagerly read. As will be seen, the Lucasian professors played a role in this recovery. The actual shift of notational use began in 1817 when George Peacock was appointed moderator for the annual Senate House mathematics examinations. He favored the differential notation in calculus and wrote his examination questions using it. This caused a major uproar at Cambridge, which included the prediction that he would never again be allowed to moderate an examination. Indeed, in the next year, the mathematical examinations returned to its previous use of the fluxional notation. But in 1819, Peacock was appointed moderator along with Richard Watkin, who also used the differential notation in his calculus questions. This same year, William Whewell, an earlier critic of Peacock, published the first book on applied mathematics written in English, Elementary Treatise on Mechanics, which used the differential notation exclusively. In 1820, Whewell was appointed moderator along with Henry Wilkinson, and this examination fully used differential notation. Peacock was once again appointed moderator in 1821, and the revolution was complete. Cambridge University had many great issues to deal with during the century. One of the most notable was the religious test that had long been in force. Religious issues in general had been an integral part of Cambridge history since its founding, but the problem was brought to a head in 1856 when the Cambridge University Bill did not include provisions for the usual declaration of faith, with the exception of the degree of divinity. For the next 15 years, the arguments to change a 200-year-old tradition were heard throughout England. The Test Acts ended in 1871, but formal prohibition of Catholics from attending Cambridge was not abandoned until 1892. 3 years later, Rome announced its permission for Catholics to attend Cambridge and Oxford, with certain restrictions. By 1899, 45 known Catholic students had enrolled at Cambridge. This number grew slowly to 130 by 1929. Lucasian professors were involved in the long and loud discussions over this issue, with major roles played by Isaac Milner, Thomas Turton, and George Stokes. The first Royal Commission was established in 1850 to reform the universities. Of its many recommendations, the one which was the most difficult to accept by the schools was that of how the Council of the Senate should be organized and how its members would be chosen. In 1870, there were 17 colleges in the university. Today, there are 31. The 19th century saw great advances in science on many fronts. The basis for today's knowledge was set down in new and as well as old ideas. Physics and mathematics pushed forward, while new areas opened up. For example, during the century, dinosaur fossils were unearthed. In 1856, in the Neander Valley in Germany, skeletons of early humans were discovered, the Neanderthals. 12 years later, in France, the remains of Cro-Magnon man were found. These discoveries opened new ideas concerning human history, creating new fields of study. The origin of species by means of natural selection or the preservation of favored races in the struggle for life by Charles Darwin was published in 1859. In biology and chemistry, a number of major steps took place in the 19th century, including biology, anesthesia, the germ theory of disease, and in chemistry, the fabrication of plastic. Anesthesia in the form of ether was first used in 1842 by Crawford Long, then again in 1846 by William Merton. Long did not report his practice until 1849, but Merton published it in 1846, so he is usually acknowledged as the discoverer of anesthesia. This advance permitted today's surgery. Louis Pasteur and Robert Koch did their work on immunization during the century. Eddie McCarthy of Dartmouth, Massachusetts, was the first person to benefit from William Röntgen's discovery of X-rays. His broken arm was set using X-rays 3 months after the discovery in 1895. In 1845, Adolf Kohl, using chemical elements, first synthesized an organic compound. Frederick Kuckel demonstrated in 1861 by the use of diagrams that the source of the properties of an organic molecule is its shape. 4 years later, Alexander Parker created a process to make the first plastic celluloid. A great advance for chemistry as well as physics was Dmitry Menedev's version of the periodic chart of elements, published in 1869. It was incomplete, thereby providing for the prediction of several new elements. These predictions came to pass with discoveries in 1875, gallium, 1879, scandium, and 1885, germanium. Jacob Bigelow published The Elements of Technology in 1829 using the word technology for the first time. Carl Beans drove the first automobile in 1885, and in 1877 the Bell Telephone Company was founded, just 2 years before the practical electric light bulb came into use. During the century, electricity was brought into the home. Charles Babbage, a Lucasian professor, invented the first true computer in 1822, calling it the difference engine. In 1832, he designed a second one, the analytical engine, that was far ahead of its time. The need for quality of the parts outstripped the manufacturing capability of the time. The two engines were the grandparents of today's modern computers. In the field of mathematics, one of the most important advances was in geometry. In 1854, Bernard Riemann set down a new version of geometry that included Euclidean geometry as a subset. It did not invalidate Euclid, but rather put his work in a broader context. Riemann geometry allowed for curved space to be mathematically useful and understood. It is analogous to an individual who has always believed the earth to be flat, accepting it as curved. Over short distances, it certainly appears flat, but over long distances, it is curved. The real value of this advance was not fully appreciated until 60 years later, in 1915, Albert Einstein used it to explain gravity. Some other important mathematical advances were the mathematical theory of heat produced in 1811 by Simon Denis Poisson, whose special use of brackets in mathematical notation would play a critical role in the mathematics of quantum mechanics in the 1920s. In 1815, Augustin Louis Baron Schauke managed to create mathematics that describe turbulence, a still difficult problem in fluid mechanics. A Lucasian professor, George Stokes, developed equations describing how one fluid passes through another. These equations, known as the Navier-Stokes equations, are fundamental tools in today's world of fluid mechanics. Physics moved ahead by leaps and bounds, setting the stage for the 20th century, which shook physics to its deepest levels. Thomas Young started in 1801 with the publication of an experiment proving that the nature of light was a wave. He used the well-known slit experiment that demonstrates interference, a characteristic of waves. He used the word energy for the first time in 1807 as he introduced the concept. Also in 1807, Hans Ørsted began looking for a connection between electricity and magnetism. In 1820, he published the fact that a magnetized needle is affected by electric current. This seemingly insignificant event grew through the century into a powerful understanding of the four fundamental forces of nature. In the last half of the 20th century, billions of dollars have been spent in research centered around these forces. From 1824 through 1865, work in the area of thermodynamics was pursued, resulting in the articulation of the main laws of thermodynamics. The efforts in 1842 to 1847 resulted in the understanding of the conservation of energy, that energy is neither created nor destroyed, but merely transformed. The concept of potential energy was discovered in 1853, bringing the understanding that the position of an object contained energy that could be changed into usable energy. In 1905, Albert Einstein showed that energy and mass are in fact the same thing. The publication of James Clerk Maxwell's Electricity and Magnetism in 1873 set down the basic laws of electromagnetism and predicted radio waves. Finally, in 1888, Heinrich Hertz detected and produced radio waves. In 1873, George Stoney estimated the charge of an electron and gave its name that it's known by today. The electron had not yet been discovered, but his estimate was very close to today's measurement. In 1885, Johann Balmer discovered the formula for the spectrum of hydrogen that bears his name. Niels Bohr used it in the next century for his model of the atom. Then Paul Dirac discovered the formula using quantum mechanics to show the correctness of his own work. Albert Michelson invented the interferometer in 1881. 6 years later, he and Edward Morley used the interferometer to measure the speed of light. They expected to use the difference between the two measurements to get the speed, but instead, they showed that the Earth did not move through the ether. They were unable to explain this discovery. So the problem lasted into the beginning of the 20th century. They had in fact shown that the ether did not exist. In 1890, Heinrich Lorentz proposed that atoms might consist of charged particles that produce visible light through oscillation. In 1896, Pierre Zeeman discovered the Zeeman effect, where one sees the splitting of spectral lines of a gas that have been subjected to a magnetic field. Lorentz used his 1890 theory to explain this phenomenon. He then calculated the mass-charge ratio of the electron within the atom. The next year, Emil Weichert stated for the first time that there may be particles 2,000 to 4,000 times smaller than the hydrogen atom. John Joseph Thomson discovered the electron in 1892. It was not until 15 years later that electrons were shown to be part of the atom. The 19th century was an exciting time for one major discovery after another in many different fields. But whereas technology was rapidly pressing forward, the science was still laying the groundwork for the discoveries that would not take place until the 20th century. Several of the Lucasian professors made historic contributions during this century. Thank you for listening to this segment of the Lucasian Legacy, the Lucasian Professorship of Mathematics at Cambridge University by Robert Bruen. To learn more or support this podcast, go to lucasianchair.org or our Instagram account, Lucasian Legacy.